Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm pleased to introduce our next speaker, Yana Demetrio from University of Washington, where she's associate professor in the math department. She got her PhD at MIT in 2003 with Alan Edelman, whom we heard about in the preceding talk. After that, she was a Miller Fellow at UC Berkeley until 2006, and then came to UW. She's worked in various fields, probability perhaps most recently, but also numerical analysis, combinatorics, and linear algebra. And she's going to tell us about a regular stochastic block model.
Thank you, Russ, for the very kind introduction. And I'm sorry, but I'm going to have to correct you. It's not the same Alan Edelman. I mean, it's actually not Alan Edelman. It's somebody else. Edelman Green. Is that what you were?
Oh.
Yeah.
Oh, really?
It's a different Edelman. Yes. Seems to be a popular name. All right, so it is my great pleasure to be talking about an ongoing problem that we're working on at UW. This is joint work with my students Gerandy Brito and Shirshendu Ganguly, and with my colleague Chris Hoffman. And for part of this, we were joined by Linh Tran, who was a postdoc at UW up until this year. So we're talking about a regular stochastic block model. Oops. I guess this one. Or not. All right. So I'm going to give you a quick overview of what I'm going to tell them, what I'm going to tell you, then I'm going to tell you, then I'm going to tell you what I told you. So I'll give you a quick introduction to the field. Actually, it's not so quick. It's probably going to be somewhere between a third and a half, really, of the talk. About independent edge binary SBM, which actually will be partly described in the introduction as well. And then I will tell you how you change that definition to make it regular. And I will talk about the issues that arise, why certain things become easier, why certain things are slightly harder, but overall the problem is much more tractable, it seems. And then I'll tell you about current and future work. All right, so let me, without further ado, talk about the clustering problem. This is a very well-studied problem. Some would say that it's been studied to death, but it's still not solved completely, so it's still worth talking about. In fact, it's interesting to people. The idea is to input a network with clusters with some sort of properties, possibly overlapping, although I won't be talking about this today. And the idea is to be able, through some algorithm, to detect or recover these clusters accurately and efficiently. I'll talk about what it means to detect and to recover in a moment. But it has applications in many places: machine learning, community detection, synchronization, channel transmission, and so on. And there are many questions that are still open and quite subtle, especially in the case when overlap is possible. Which again is not going to be the case that I'll be talking about today. There's a huge body of work, as I mentioned, and it overlaps many subjects, many fields: optimization, EE, theoretical computer science, and math. There are two approaches that one can take to studying this problem. One of them is to study actual networks and try and see if your algorithm actually can detect the clusters. This is Zachary's network. It's the network that described the interactions between members of a martial arts club that suffered at some point a division, and some people went with the old instructor and some people moved to the new. And essentially this picture describes how the secession took place. This is a group that went with, or rather stayed with the instructor, and this is the group that seceded. This is a network that's been really studied to death. It's used as a benchmark for pretty much any algorithm. Oh, look, my algorithm can actually cluster Zachary's network correctly, and so on. The other approach is to focus on studying idealized models of networks, like, for example, ones produced by Erdős-Rényi, and this is also known as the problem of studying spherical cows. That's what we're going to be doing. So here's the stochastic block model, or SBM for short, also known as the planted partition model, if you've seen that in the literature. Essentially, it says the following thing. It's very easy to describe. You have to consider k Erdős-Rényi graphs with sizes ni and probabilities pi, independent and non-overlapping. And aside from that, you can put on the join of their graphs a multipartite. And by multipartite, I mean basically that any two vertices that are in non-adjacent, not in the same cluster, get joined by an edge with probability q. Okay? So you have some sort of cluster, some sort of k clusters, and then on the outside of them you put a multipartite Erdős-Rényi with some given probability q. The question then becomes, under what sort of conditions on all of these parameters, oh, and this should have been actually a small case k, sorry, can one recover or detect the presence of the partition? Recovery here is understood as being, generally it's understood as being complete recovery, although sometimes weak recovery is considered, where you expect to recover all but sublinearly many of the nodes. Detection means that you're able to say if you believe that there's some structure like this at work, or if the network is just random. Okay, so the possibility of recovery has been studied generally via the maximum likelihood estimator and convex relaxations thereof. Recently, though, there's a new approach which is described by using multiple structure matrix algorithms. So you think of the adjacency matrix as being sparse plus low rank. Sparse being the outside plus, and the low rank actually identifying the clusters. So being essentially a matrix that corresponds to, instead of clusters, just taking cliques at the same nodes. So this is one of the references. There are Vinayak Oimak and Babak Hasibi. There are more general, the most general analysis, so via impossibility via information theoretic bounds, plus a convex relaxation for the maximum likelihood estimator, is fairly new. Well, it's actually very new. It appears in a paper by Chen and Zhu from 2014, and it gives various order sharp bounds. So that means that they don't get any constants, but the order of the thresholds is found for various regimes. The only case that has so far really been solved in terms of various thresholds is the two equal cluster binary case, and one can say that most of the work has been done by an alumnus of the Microsoft research group, and that's and his two students, well, two ex-students, I should say. So I'm referring to Elhanan Mossel and to Joe Neiman and Alan Sly. Okay, so here's a dictionary of terms. I will talk about a strong recovery regime when it is possible. There are algorithms that will give you the partition completely. Weak recovery regime means that you don't get it exactly, but you get essentially up to sublinear many nodes labeled correctly, and others may be mislabeled. There's an approximation regime where you get a fraction of the nodes correctly. The fraction is bigger than 50%, but the rest may be mislabeled. Then there's a detection regime where you can guarantee to get just above 50% of the nodes correctly labeled, but you can't quantify that. You can't say how much better you can do. And then there's the impossibility regime where it is impossible to do better than guessing, essentially. And generally, it's because of indistinguishability. I'm not even sure that that's a word, indistinguishability reasons, where your model is essentially indistinguishable from that of an Erdős-Rényi with twice as many vertices and the according adjusted probability. So the nomenclature in the field is varied, and it seems that everybody uses their own preferred words. I'm using this, which is kind of a combination between Mossel-Neeman-Sly, Massoulie, and Abbe, I'm not sure how to pronounce his name, Bandira and Hall. I should be able to pronounce his name because I know him, but it's embarrassing. Okay. So this is a nomenclature. I hope you'll be able to remember it. So this is the exact definition for the binary stochastic block model. You start with 2n nodes, and you pick n of them to be labeled 1 and the others -1 uniformly and independently. And then you add an edge between vertices with the same label with probability p, which sometimes can be, and in fact it's going to be a function of n. And then outside of that, so you add edges between vertices with different labels with probability q. And you can call the resulting graph model G2NPQ. I guess I'm going to have to use both of these somehow. I'm not sure. OK, so let me talk about briefly about the strong recovery regime. You will need to have P and Q at least logarithmic in n, because otherwise you will get, well, depending on the constant, with constant probability you'll get isolated vertices, and those you cannot classify. There's a bunch of people who have worked on this problem and have made similar contributions, and it was solved almost completely by Bandira and Hall in 2014, and completely by Mossel-Neeman-Sly a few months later. In other words, if you have this regime plus some tiny conditions, I guess, which I'm going to show you in a moment, you can do complete recovery. So this is the state of the art. And when you see MNS, it's going to be short for Mossel-Neeman-Sly. You'll see that a lot in this talk, which is why I've just felt like I could shorthand it. So the state of the art is a rather complex characterization, but certain cases can be made more explicit. So for example, if you think of Pn and Qn as being roughly constant times log n over n, although the constant can fluctuate a little bit, then strong recovery is possible if and only if this happens. So in other words, if this number here, or if the sequence of numbers here is strictly positive at all times, then you can do, then you have strong recovery, and it's necessary for strong recovery to be at least non-negative. Okay? This matches the Bandira and Hall results, but they weren't thinking in terms of letting the constants fluctuate, and therefore this is what they got. They didn't get this.
So,
yes.
When you say strong recovery is possible, does that include a statement about computational complexity?
So it's a little vague. So Bandira and Hall were showing that this is possible for slightly different conditions. It seems that the algorithm that MSN has come up with is almost linear in the number of edges. So that would suggest yes.
But I'm sort of
it's not. There's no.
Is that what you're focusing on here, or just
no, just existence, possibility of strong recovery.
Good.
Yes,
Thank you.
yeah. But it seems like that's the case. I think that they will probably do a complete analysis. In fact, I was going to say something in a little while, but it seems like that might be the case. Okay. So there's a weak recovery regime in which you can recover up to sublinearly many of the vertices, and this is again MSN 2014, MNS, sorry, 2014, and it's a very nice result, which essentially says that you have to have the probabilities slightly better than 1 over n. You want them to go to infinity. NPN and NQN have to go to infinity, and you have to have this extra condition attached. So again, not sublogarithmic. You cannot. Sorry, you can have them sublogarithmic, and you cannot, because of that, you cannot hope for strong recovery. That's why you're. And it seems that the reason why you do not get, or you, in a sense, what you cannot get, is caused by the fact that some vertices may be mislabeled in the sense that they might actually be labeled 1, but have more connections to the wrong set, to the other set. Okay, so
is
this is
there
the
really a minus sign in the second term?
Oh, I'm sorry. This should be a plus sign. Yeah, it's just this should be an identity. Yes. So this is a plus. Apologies. Okay. Then there's an approximation regime, which actually was first studied by Koja-Oglan. I hope I'm pronouncing that correctly. Who showed that if you consider P and Q to be A over n and B over n, and you have this extra condition for some large constant, then you can detect, so bear with me, I'm going to talk about detectability next. You can detect the presence of the partition, but the fraction of recovered vertices is bounded. You cannot do better than a constant fraction of the vertices, which fraction depends on C. And then some other M and S from 2003 algorithm, there are others that I'm going to talk about soon, use belief propagation to show that this fraction is actually achievable. So yielding thus an approximation regime in which you can get a certain fraction of the vertices correctly. When C approaches 2, the constant approaches a half, which is why nobody expected that any kind of approximation could be done in the lower range. Okay, finally, detection and impossibility. Again, Mossel-Neeman-Sly have been all over this problem. So it turns out that they had a challenger, Massoulie, at the same time independently obtained a different proof for this, but they showed that when we are in this regime of P and Q being O of 1 over n, specifically A over n and B over n, then there exist polynomial time algorithms to solve, to find a correlated partition if and only if this identity is true. This is a threshold that has been conjectured by Dissel-Krzakala, Moore, and Zdeborova, and has been reinforced several times since then, in particular in 2012, when Mossel-Neeman-Sly showed that if you're under that threshold, then the graph is indistinguishable from an Erdős graph with 2n vertices and average, the average of the two. Oops, there should be an n there. I apologize. No, there shouldn't be an n. No, because it's correct. And hence reconstruction is impossible because if you cannot distinguish, you cannot detect. Okay, so complexity, as mentioned, it's not written in stone, but it seems that there's polynomial time strong or weak reconstruction. Belief propagation is also efficient. Detectability was shown to be polynomial time by both groups who showed detectability. So the bottom line is that there seems to be no regime where reconstruction is possible, but not in polynomial time. That's a very interesting thing, because it runs contrary to the widespread belief that there are hard regimes if you have more than 2 clusters. Okay? Perhaps clusters that are growing or not linearly in n. And it has a connection to the minimum bisection problem, which again is known to be hard. So it's kind of an interesting, yes, Chris?
I'm sorry, but I got lost. If there's this graph that is somehow randomly generated and somebody wants to answer all these questions, what is the information that that person has access to?
The adjacency matrix. Yes, thank you, sorry. So you have access to the graph. You just have to test whether it's a large graph. You need to test if the model that is being generated from, is the one described here. Okay. So let me introduce this notion of a regular stochastic block model. So basically, we do the same thing, except that now instead of taking Erdős-Srény graphs, we take uniformly regular graphs. So for integers n d1, d2, you take 2 d1 regular, uniformly regular random graphs of size n, and you connect them by a bipartite n and d2, also uniformly random. Everything is independent of the other things that you're doing. And of course, the question is why? Why would you do something like that? And of course, the answer can be manifold. the structure in such a model is a lot more rigid, can you say a lot more than you could before? Can you do recovery in other kinds of cases? Can you do recovery in the so-called lower regimes when you have P and Q smaller? There's also edge dependence. How does that affect things? Because before, edge independence actually was playing a pretty heavy role in the calculations. Do you use the same methods or you come up with others? And of course, lastly, because it's there, we're in a math department. Okay, so the first thing to note, if you remember, I mentioned that there is an impossibility regime for the Erdős-Rényi stochastic block model, and that is that if the relationship between the two probabilities is of a certain nature, then you cannot distinguish essentially between your model and just a bigger Erdős-Rényi model with the average of the probabilities. Here, you can always distinguish between this model and just a random uniformly regular D1 plus D2 graph. Your model is also of that type. So if you look at the fact that you have two D1 regular joined by a D2 regular, that means that that graph is actually D1 plus D2 regular. However, it's a very different distribution than that. So you can tell, basically. And the reason is that if you count the number of graphs that you have in both sets, it's exponentially smaller. So this is not, here's where things diverge for the first time. Of course, unfortunately, distinguishability has no computational value. What we would like, really, is to prove uniqueness of the partition. So in other words, if you generate your graph like this, you would like to know that there's basically no chance that it can also be expressed in the same way with a different partitioning of the two classes of vertices. Okay? Then you can hope for recovery. If it turns out that you don't have uniqueness, no choice, no chance of recovery. Okay, so that's what one would like. And of course, we've made progress toward this. Kind of very interesting progress, because we can show uniqueness when D2 is less than D1, but for huge sizes, sizes of D2. The interesting stuff happens when D2 is small, so that's why this is very partial progress, but we're not going to stop here. The idea is roughly to improve our results on this lemma, which is the overlap lemma, and to which I'm going to refer again, which says that if the partition exists, if the second partition exists, if you want, in some case, then the smaller swapped set must be large. So if you have two such partitions in your graph, then the set of overlaps must be really large. So in other words, you can't just swap a few vertices and hope that you get a second partition. We're working on improving this from upping the fraction from 1/2d2 to 1/2. If you can show that, obviously, if you can show that you need to swap at least 1/2, then that's, or rather, 1/2 is a barrier because it's the smaller of the two sets. It's very easy to explain why this happens. So suppose that this is your left, let's say, D1 regular graph. This is your right D regular graph. And suppose that a second partition is possible, which essentially swaps the set of vertices in B to the set of vertices in C. Then it turns out that, and it's a trivial, actually, observation, that if you pick a vertex V in B, the number of connections that it has to vertices in A has to be the same with the number of connections to vertices in D, because you're about to swap things. And this has to be also, the new swapped thing has to be still D1 regular. The problem is that D1 and D2 are different, and we know that V cannot have more than D2 connections. In fact, V has to have precisely D2 connections to C union D. So it cannot have more than D2 connections to D. However, if this set is small, the chance of getting a vertex whose all D1 connections are to A rather than to B is significant. And at that point, you would have to have the same degree to D, but D1 is bigger than D2, so you can't do it. Okay, so this is essentially a good heuristic for the argument of why you have to have uniqueness of the partition in such a case. Okay, so I think I just explained this. Then we have, and this is, I think, the only proof that I'll show. I'm going to zoom through the rest of it. There's an easy spectral regime. The fact that you are working with a D-regular graph allows you access to a whole host of very interesting simple linear algebra properties. So as a consequence of these properties, we have this theorem, which says that if the difference between the 2 degrees is bigger than this quantity here, then the second largest eigenvalue of the adjacency matrix is D1 minus D2. The first eigenvalue of the adjacency matrix is D1 plus D2, because this is a D1 plus D2 regular graph. But the important thing here is that the second largest eigenvalue is D1 minus D2 with multiplicity 1 and with eigenvector corresponding to the correct partition. So in other words, if you have the adjacency matrix, if you are in this regime, then basically you find the second eigenvector and you're good to go. That's going to give you the partition. Okay? And also, the consequence is that the partition is recoverable. This is due to the fact that the multiplicity here is 1. If you were to have 2 distinct partitions, both of those would have to be eigenvector, or would have corresponding eigenvectors with eigenvalue D1 minus D2. However, the multiplicity of this eigenvalue is 1. Okay? So the partition is unique and recoverable. And it solves the mean bisection problem for this model. Like I said, the proof is really simple. It's just linear algebra. These 2 are facts. You can check them. Then you can split the adjacent. Sorry? Sorry. I'm thinking if people are falling asleep in the audience, they could spend some time actually checking that these are facts. Split the adjacency matrix like this. So now you have 2 D1 regular graphs, and then this is the bipartite D2 part. These are adjacency matrices of random regular graphs, and this is the random adjacency matrix of the bipartite regular graph. And now you just do spectral analysis on them, essentially. So you calculate this and bound it from above. Actually, I should have probably put an absolute value here, but it's a symmetric matrix. I should have put an absolute value. This is what happens. So if you look at a vector that's orthogonal to the first eigenvector and the second eigenvector, then the value that this quadratic can take is at most this. And this is strictly smaller than D1 minus D2 by the condition. How can you show that? Essentially, you split the matrix like I said, and then you make a gross overestimate. Essentially, you split it into these 2 parts. And you use the fact that at least for the, this should have been an A1. Apologies, this should have been an A1. So remember that A1 is just the part corresponding just to the 2 D1 regular vectors, D1 regular graphs. And on each one of them, you have, due to Friedman, a very nice result on the second eigenvalue. You bound that, and you get that the overall bound is 2 square root of D1. The same thing holds true for the bipartite graph. It has been shown that a similar bound on the second eigenvalue is true by Putter in 2013. And therefore, you put it all together and you get this. It follows, therefore, that the second eigenvalue is D1 minus D2 with multiplicity 1, etc., etc., etc. So this is an easy regime, or is spectral. That's not the only case in which you can get strong recovery in this model. That's just an easy regime, and actually we've done that because it's easy to explain. But it turns out that essentially using the methods of Massoulie we can, adapting, I should say, the methods of Massoulie, we can find this theorem. So if the difference between the degrees squared is bigger than d1 plus d2, then the partition is strongly recoverable in polynomial time. Now, mind you, Massoulie had detectability. So this is strong recovery, much stronger. Essentially, the methods are adapted to work for the case where you have a different kind or almost independence of edges, because d1 and d2 are fixed, and you can use the configuration model for the uniformly random regular graph. But it's not exactly trivial work. However, you get a lot more. So Massoulie used the matrix of self-avoiding long walks, in contrast with the MNS strategy of using the matrix of non-backtracking long walks. The difference really is that in the second case, the entries of the matrix are bigger and the method is not spectral, whereas the method of Massoulie is spectral, so we used that because it was more accessible to us. And this is all I'm going to tell you about how to prove it. I had several lemmas, actually, that I was hoping to show that I'm obviously not going to have time for. The idea is to do a local analysis. You have to show that no cycles are close. And of course, this is known for the deregular graph. It takes a little bit more work to show it in the context of this model where you put regular graphs together. And this holds. So cycles are not as close as C log n. So cycles are far apart. And then there's, of course, the connection between path structures and labels of the neighborhood, which in our case, given that we have a regular graph, is very simple to establish because we know what the neighborhoods look like. We know exactly what the neighborhoods look like. Whereas in the case of Erdős-Rényi, it's still an element of randomness. Whereas here it's an exact count. And finally, the true important ingredient is to do the following thing. You have to show spectrum separation of the first two eigenvalues of this matrix, the matrix of self-avoiding walks of length L, from the rest of the spectrum. So the first eigenvalue, and maybe I'm going to show that lemma. So if you show spectrum separation of the top two eigenvalues, then essentially you will get a partition that is correlated with the the original partition, except that in our case it's not just correlation. In our case is allows you to recover the original partition up to n minus little o of n. And then you can correct the blemishes by majority rule. Okay, all of them. And then you get complete recovery. This is pretty standard technique. Okay, I'm going to just show you this. So this is the core of the argument, really. So we show that the graph is tangle-free with high probability. And if that's true, then the following estimates are true for these two quantities. So e to n, remember, is the vector of all ones, and sigma is the vector that gives you the signs. If you look at what happens here, you see that these two, if you scale them down by square root of n, they will become unit vectors, both of them. And so this n here, and this n minus big O of n to the delta, where delta is small, over here, will essentially disappear. And what you're left with is telling you that this is essentially going to go to the first eigenvalue of SL, which is going to be d1 plus d2 to the L. And this is almost an eigenvector. And similarly, this will go to what will turn out to be the second eigenvalue of this SL, which is d1 minus d2 to the L. And this is close to an eigenvector. You can actually show that this is polynomially close to an eigenvector. Provided that you can show good separation from the rest of the spectrum. So if you can show that for any other vector that's orthogonal to these two guys, then the same estimate, which is much, much smaller, then you're done. And it turns out that that's true. It turns out that if you look at unit vectors that are orthogonal to those two, then the estimate is much, much smaller. Notice that here you have a d1 plus d2 to L over 2. you essentially want that to be smaller than d1 minus d2 to the L. And that's what gives you the condition. Okay. Finally, then there's a question of, OK, so we know that the second eigenvector is going to be giving you the partition up to sublinearly many vertices, which are going to be incorrectly labeled. But you could have two partitions for which both of which have the property that the second eigenvector does that. Well, no, because in that case, the two partitions overlap very much, more than we've shown is, overlap very, the swap is very small, and we've shown that the swap has to be relatively big. This was the last ingredient. OK, so this is just the recap. We showed that strong recovery is possible in polynomial time, and we believe that recovery is actually always possible, because uniqueness, that's what uniqueness tells you, that recovery is always possible. This is a rigid model, so if you have the graph, you could in principle just test all the vertices. Of course, that's not efficient, but you could test all possible pairings and see if it works. So that's very different from before. And the question is there a threshold for the complexity here? So we've shown that recovery is possible in polynomial time in a certain regime. We believe that, and we believe that we'll be actually able to show that recovery is always possible. And because, this threshold is given by the method. We have no idea if it can be pushed down just yet, but we're working on it. But it's also possible that this is actually an efficiency threshold. It's perhaps lower than this, you cannot get polynomial time algorithms. And of course, then the idea is to generalize to multiple clusters. And I'm going to stop here. Thank you.
Questions?
Yes, please.
I have a question, but it's not mathematical. I understand that these results are asymptotic. Mm-hmm. So in some sense, they should call for large networks. Okay, so I'm thinking about something like Facebook. But in Facebook, when I try to think about communities, I would guess that there's actually a very large number of communities.
Yes.
Not just two or
yes.
three or a small finite number of very big.
Yes, and there's overlap as well, yeah.
So basically, what are good, practical, motivating examples of a large network which only splits to either two or a small number of communities?
That's why I talked about spherical cows.
What?
That is why I talked about spherical cows. Yes, in general, you're completely right. So the idea is to get results that are asymptotically true for many clusters, for overlapping clusters, for clusters of different sizes, and so on. And there's a whole body of literature on that. No thresholds. So thresholds that are perhaps at best order thresholds. So we started off with this example because there's hope here that one can analyze it completely. Higher than that, probably not. However, I am actually working with Mariam Fazel and with a couple of her students on a problem just like that. So we're actually making some interesting progress. Generally, the algorithms that will produce the clustering will be so some sort of convex relaxation of MLE. And it turns out that in certain regimes, they perform well. And the question is, what are these regimes? And generally, the conditions that you get involve all the parameters in the problem. So they're horrendous. So then you have to start saying, OK, let's see if the clusters are equal. What does that mean in terms of the probabilities associated to each cluster? If the clusters are very separated, how can I play the probabilities to get an impossibility regime and things like that?
Just one relevant example. Of course, the rough model is a very rough approximation, but clustering into two is something we want to do all the time. For instance, just differentiate legitimate websites from spam websites. So that would be two clusters, and there are lots of links between legitimate websites and each other, and lots of artificial links created between the spam websites, and also some links that go between these two groups, but those may be different nature, and this kind of graph structure is the basis for using, one of the tools, I should say, for this kind of distinction. So, it's the real picture is very different from these beautiful models.
Yeah.
Okay, so that's nice. So actually, there are some real examples.
There are lots of real examples where we want to distinguish between two. So that part is real. These, random graph models are approximations.
I mean, in that case, you don't really have two clusters, right? Because the spam may consist of many different spam clusters.
Yeah.
Right, but
Or not clustered points even, yeah. Which is
The thing that you want to make a binary.
You want to make
partition.
a binary partitioning, right? And so the graph.
not necessarily with equal weight or anything, yeah. Yes.
What do these counterexamples with D2 equals 2 look like, just so I can get some idea of when it's...
You can find counterexamples. Essentially, the idea is that for D2 is equal to 2, then you don't have connectivity. So you can have long cycles of the same length, and you can essentially swap those.
Oh, okay.
You can construct examples. Yeah.
So you're saying you think it's a theorem that for any D-regular graph where D is...
I think we found,
there are
yes. So there's a
partitions.
theorem that says the following thing. If D is greater than or equal to 3, then with probability 1 AAS, yes, the graph is connected.
No, but I mean, for what you strongly suspect is true, you strongly suspect that it's a deterministic theorem that if you have a D-regular graph, there is...
Yeah, so like I said, you can actually find examples for D2 equals to 2, where the probability of encountering a graph that has two possible partitions is not 0, is not.
But he's not asking about the probability.
I'm sorry, I guess I don't understand.
He's asking about the uniqueness of partition for D bigger than equal to 3.
Oh, what's the question?
Are you saying that you suspect that it's deterministically true that any D-regular graph...
Not deterministically true. I think that it is true with high probability. You can always find it, like, for example, if you think of a square, okay? So you have n, that n is even, so you just put n over 2, n over 2, n over 2, n over 2, and then you just put, there you put, I guess, g over 2 or something like that, regular examples, and then between them, bipartite d over 2, bipartite d over 2. In this case, d1 is equal to d2.
Okay.
But you can imagine other cases where it works.
But the idea is these would occur with
Yeah.
T.
Yeah. So there's no reason to believe that this is deterministic. I think that it's with high probability. So
Okay.
with vanishing probability, do you expect to encounter a second partition in a graph that has one? Sorry, I didn't understand you.
Any other last questions? Good to thank Oyana again.
Thank you.